So let us solve some problems based upon what we discussed last time. Okay. So this is first problem. Capacitance of a parallel plate capacitor with air as a medium is 6 microfarad. With the introduction of a dielectric medium, the capacitance becomes 30 microfarad. Okay. The permittivity of medium is, this is very simple question, right? So capacitance becomes C dash. We can say when dielectric is inserted, what happens to the capacitance? It is dielectric constant multiplied by capacitance. Okay, it is dielectric constant multiplied by capacitance, right? So from here we get dielectric constant. So K is equal to what? C dash divided by C. It is equal to 30 divided by 6, 5 microfarad. But what is asked? The permittivity of the medium is asked. Okay, so permittivity is just epsilon is just equal to epsilon 0 K. Okay, so this is just a calculation. Epsilon naught is 8.85 multiplied by 10 raised to minus 12 multiplied by 5. So this is 9 times 5 we can say. Okay, almost 9 times 5. 45 multiplied by 10 raised to minus 12 or 4.5 multiplied by 10 raised to minus 11. Okay, or you can say, okay, this is 4.4 something multiplied by 10 raised to minus 11, or you can say it is 0.44 multiplied by 10 raised to minus 10, right? It's option C. Next question. Two parallel metal plates having charges plus Q and minus Q face each other at a certain distance between them. If the plates are now dipped in kerosene oil tank, the electric field between the plates will, you tell me, become zero, increase, decrease, remain same. Parallel plates are inserted. Okay, initially there was air between them. Now they are inserted in a kerosene tank. What will happen to the electric field? Will it increase, decrease, remain constant? So initially electric field is sigma divided by epsilon naught. When they are dipped in kerosene, electric field becomes sigma divided by epsilon, which is epsilon 0 K. Okay, the dielectric constant of any other medium is greater than air. Okay, it is greater than air except for vacuum, right? So if K is more than 1, you can say what will happen? E dash will be smaller than E. So it decreases. So a parallel plate condenser with oil between the plates. Dielectric constant of oil K is equal to 2. Has a capacitance C. If the oil is removed, then the capacitance of capacitor becomes. What will happen? So here we know C is equal to what? Epsilon naught Ka divided by D. This is the formula. If oil is removed, right? Oil is removed. So air will be left between the plates. So then capacitance will become epsilon naught A upon D, right? So which is equal to, I can say, 1 by K times epsilon naught Ka divided by D, which is 1 by K times the original capacitance, right? It's 1 by K times C. And what is K? K is equal to 2. Okay, so it is C by 2. Two thin dielectric slabs of dielectric constants K1 and K2. K1 is less than K2 are inserted between plates. Okay, so these dielectric slabs are inserted between two plates of parallel plate capacitor as shown in the figure. The variation of electric field between the plates with with distance d as measured from plate P is correctly shown by. So yeah, what is the answer? What will happen to the electric field where you have a dielectric? It will decrease, right? The electric field will decrease. Okay, and how does the electric field decrease when you insert some dielectric? So electric field in a dielectric of constant K, we can say it is electric field in air divided by K. Okay, so here, here and here the electric field will be same, it's electric field in air. So here it will decrease and here it will decrease. Okay, now it depends on the dielectric constant. So it's given that K2 is greater than K1. So electric field in this region will be less than the electric field in this region. Okay, so it will start off with some value, then it will decrease. Okay, it's decreasing here. Okay, in this diagram and in this diagram, it's decreasing here also, but it will not become zero. Okay, it will not become zero. These are not conductors. Okay, so it will decrease, and again in the other one also it will decrease. Okay, so electric field has some value, then it decreases, then it comes back to the original value, again it decreases. Now dielectric constant of the other one is greater, so it will dip furthermore. Okay, it will look like this. See the graph. It's option C. Parallel plate capacitor of area A, plate separation D, and capacitance C is filled with four dielectric materials. Okay, there are four dielectric materials in this capacitor having dielectric constants K1, K2, K3 and K4 as shown in the figure. If a single dielectric material is to be used to have the same capacitance C in this capacitor, then its dielectric constant K is given by. This is the question. Okay. So first of all, let's find out the capacitance of this capacitor. So see, here we have these three capacitors. Okay, we can say these three parts, they act like three different capacitors, and this one is fourth capacitor. So these three are in series or parallel, right? These three are in parallel combination, so their capacitance will get added. Okay, you can draw it like this if you like. This is 1, 2, 3. Okay, so this is, here you have dielectric constant K1, K2 and K3. So these three are in parallel combination, and the fourth one is in series. Okay, series with parallel combination of these three. So first of all, let's find out the capacitance of their parallel combination. Okay, so we know the formula for capacitance. It is epsilon naught Ka divided by D. Okay, and in parallel there is addition of capacitances. So the total capacitance of parallel combination Cp will be epsilon naught K1 A1 divided by D. D is same, and it is equal to what? Half of the D. Okay, half of distance between two plates. Okay, it is D by 2. And what about the area? Area is 1/3. Right, area is 1/3. So instead of A1, I will say it is A by 3. Plus similarly, capacitance of this one is epsilon naught K2 A2 divided by D2. But A2 and D2 are same. A by 3 and D by 2. Okay. So it is epsilon naught K2 A by 3 divided by D by 2, plus you have epsilon naught K3 A3, which is also A by 3 divided by D by 2. Okay. Then you can take many things common. You can take epsilon naught A and D common, epsilon naught A by D. Okay, then this 2 will go to the numerator, this 3 will go to the denominator. It is 2 times epsilon naught A divided by 3D. Okay, and multiplied by you have K1 plus K2 plus K3. So this is capacitance of parallel, and this one is in series with this combination. So what will be net capacitance? The net capacitance will be equal to, let's suppose Cs is the net capacitance. So 1 upon Cs is equal to, we can say 1 upon Cp plus 1 upon fourth capacitance. Okay, 1 upon C4, which is equal to 3D divided by K1 plus K2 plus K3 multiplied by, okay, plus 2 times, right? 2 times epsilon naught A, okay, plus for this one, the capacitance will be epsilon naught K into A4 divided by D4. Okay, and what is A4? A4 is A. This this dielectric is spread in complete area, but the distance between plates is half. Okay, so it is, okay, we have to write 1 upon C4. So it is epsilon naught K4 A4, which is A, divided by D4, and D4 is D by 2. Okay, so it will go in numerator, right? So D by 2. Okay, this is 1 upon Cs. And now question is, if you want to replace, this capacitance, okay, this combination with a single dielectric material, okay, having dielectric constant K. So what will be that K, right? So for that we can say the Cs is equal to, epsilon naught K times A divided by D, right? Because if you fill this total space between the two plates by a single dielectric K, then for that capacitance is, the formula for capacitance is epsilon naught K divided by D. Okay, but we want 1 upon Cs, so it will be D divided by epsilon naught Ka. So this is equal to this thing, 3D divided by 2 K1 plus K2 plus K3 epsilon naught A plus D divided by 2 epsilon naught K4 A. So again epsilon naught A D will get cancelled. So D epsilon naught A, if you cancel it out, what do you get? You get 1 upon K is equal to 3 by 2 times K1 plus K2 plus K3, okay, plus you have 1 upon 2 times K4, okay, and okay, so here if you take this 2 on the other side, okay, if you take 2 on other side, you get 2 by K equals to 3 divided by K1 plus K2 plus K3 plus 1 upon K4. Okay, so this is the answer. Option C is the answer. Alright, let us see next question. Two identical capacitors C1 and C2 of equal capacitance are connected as shown in the circuit. Terminals A and B of key K, so these are C1 and C2, they are connected like this. Terminals A and B of key K are connected to charge capacitance C1. Okay, so they are connected like this so that C1 will get charged using battery of EMF V volt. EMF means the potential difference. Okay, for now. Okay, now disconnecting A and B, the terminals B and C are connected. So you disconnect this, you connect this. Okay, due to this, what will be the percentage loss of energy? This is the question. What will be percentage loss of energy? Okay, to solve this kind of problems, I will tell you simple trick. Okay. So the trick is, see, now you charge this capacitance C1. So there will be some charge stored on the capacitance C1. When you connect this to the other capacitance, what will happen? There will be redistribution of charges. Okay. So now you have charged C1 to voltage V. Okay. But when you connect second capacitance C2, now you have disconnected the battery and connected the second capacitance. So what will happen? Suppose initially charge was Q, now the charge will get distributed, okay, on these two capacitors. So let's suppose it is Q1 on first one and Q2 on second one, right? Okay. So the initial charge will be equal to final charge Q1 plus Q2. Okay. What is final capacitance? Initially the capacitance was C1 only, and C1 is equal to, is it equal to C? Yeah, two identical capacitors. Okay, these are identical capacitors. So initially capacitance was C1 only, now capacitance becomes C2. Okay, we want to find out the percentage loss of energy. So the percentage loss will be equal to initial energy, or I will just say Ui minus Uf. Initial energy minus final energy. So initial energy will be equal to half of Q square by C. Okay, we know this formula, Q square divided by 2C, minus final energy will be what? Half of Q square divided by C dash. Only the capacitance is changing, right? Charge is not going anywhere. Charge on these two capacitors will remain same. Okay, it will be equal to Q1 plus Q2. Okay, so see, in this type of question, use this formula only, then it will be simplest. Otherwise, it will be little bit difficult. Okay, you will have to find out potential, etc., etc. There will be various steps. Okay, so delta U equals to, how much would be final capacitance? These two are connected in parallel, right? These two are connected in parallel. So it is C plus C 2C. Okay, so you have Q square divided by 2C minus Q square divided by 2C dash, which is equal to 2C. So this is 4C. Okay, 2 times 2C. So what is the answer? Q square divided by 2C minus Q square divided by 4C. So this is half of Q square divided by 2C, you can say. Okay. So it is Ui minus half of Ui. Okay, which is equal to half of Ui, half of initial energy. So how much is the loss? Half. In percentage, it is 50%. Got it? Capacitor is charged by a battery. The battery is removed and another identical uncharged capacitor is connected in parallel. The total electrostatic energy of resulting system decreases by a factor of 2, remains the same, increases by a factor of 2, increases by a factor of 2. So we have just solved it, right? So what is the answer? It decreases, it becomes half. Okay, you have charged a capacitor and you remove the battery, you connect another uncharged capacitor having same capacitance. What happens? The energy decreases to half. Half of the energy is lost. Okay, the answer is it decreases by factor of 2, right? A parallel plate air capacitor of capacitance C is connected to a cell of EMF V and then disconnected from it. Okay, so you have a parallel plate air capacitor. There is air between the two plates. So it is connected to some battery and then it is disconnected. a dielectric slab of dielectric constant K which can just fill the air gap of the capacitor. So it is completely filling the air gap, okay, is now inserted in it. Which of the following is incorrect? So you have a parallel plate air capacitor of capacitance C and you connect it to V. So what will happen? It will get charged, okay, when you connect it to a battery of potential difference V, gets charged and its energy is equal to half of CV square, half of CV square, right? Now C is given, V is given, okay. Now a dielectric slab of dielectric constant K is inserted, okay. So now what will happen? Now the capacitance is changing, okay. Now energy will become U dash equals to half of C dash multiplied by V square, right? So what will happen? See what happens, capacitance changes, potential difference also changes. What will happen to the potential? So V dash will be equal to V upon K, C dash will be equal to C times K, right? Okay. So you can find out U dash. U dash will be equal to half of K times C multiplied by V dash square, which is V square divided by K square. So this thing gets cancelled, K and this thing gets cancelled. So it is 1 by K times half of CV square. Okay. So it is 1 by K times U. So let's see, energy stored in capacitor decreases K times. So this is correct, right? The change in energy stored is half CV square 1 by K minus 1. So change in energy will be U dash minus U. This is delta U. So let's check this one. So it is half of K times U minus U. Okay. You can take U common. So U times 1 by K minus 1, or it is, you can say, half of CV square. Okay, half CV square multiplied by 1 by K minus 1, right? So this one is also correct. Potential difference between the plates decreases K times. So it is true. Okay, so what is not true? Option B is not true. The charge on the capacitor is not conserved. So charge is conserved. So why does potential difference becomes V by K? Because the electric field becomes uh, E by K, right? Electric field becomes E by K. Okay, when you insert a dielectric, it is sigma divided by epsilon naught. When there is no dielectric, when you insert a dielectric, it becomes sigma divided by epsilon naught K. So because electric field becomes sigma divided by epsilon naught K, that means it decreases K times. Potential difference is just, for a capacitor, it is just E times D. Okay, E times distance between plates. So E decreases. Okay, E becomes, E dash is equal to E by K, and therefore V dash is equal to what? V by K. Okay, that is the reason. Let's see next question. A parallel plate capacitor has a uniform electric field E in the space between the plates. If the distance between plates is D and area of each plate is A, the energy stored in the capacitor is. Tell me. This is very simple. We know energy stored per unit volume. Okay, energy stored per unit volume of a capacitor. We had found formula for it. So it is small u is capital U divided by volume. It is given by half of epsilon naught E square. So what is U? U is equal to half of epsilon naught E square multiplied by the volume. And what is volume of capacitor? So this is the capacitor, suppose. Its volume is equal to this area Okay, this area A multiplied by this distance D, A times D, right? So this is equal to half of epsilon naught E square multiplied by A times D. Option C. Next question. A series combination of N1 capacitors, each of value C1, is charged by a source of potential difference 4V, when another parallel combination of N2 capacitors, each of value C2, is charged by a source of potential difference V, it has same total energy. Okay, so series combination and parallel combination have same total energy. This is given as first combination has the total, sorry, the value of C2 in terms of C1 is then. The value of C2 in terms of C1 is then. This is the question. Okay. So we have series combination of N1 capacitors, N1 identical capacitors, each of value C1. What is series combination? CS is equal to C1 divided by N1, and parallel combination of N2 capacitors. So what is Cp? Cp is equal to N2 multiplied by C2. Okay. So what do we get? So series is charged by 4V. Okay. You have series combination whose capacitance is C1 upon N1. Parallel combination whose capacitance is N2 times C2. So now you charge series by 4 volts. So it's given that energy of series is equal to energy of parallel. So what is energy of series? Half of CS multiplied by V square. So V is equal to 4V. Okay. And C2, CP is N2 C2. So here you have half of CP multiplied by V square. Okay. Half and half gets cancelled. V square gets cancelled. So you have 16 CS is equal to CP. And now we just have to substitute CS and CP. So CS is C1 upon N1. So you have 16 times C1 divided by N1 is equal to CP. CP is N2 C2. N2 times C2. Okay. So which option is correct? We want C2, right? Take N2 on the other side. We want C2. So C2 is equal to 16 C1 divided by N1 N2. It's option D. Next question. Two condensers, one of capacity C and other of capacity C by 2, are connected to a V volt battery. Okay, as shown in the figure. So these are two capacitors C and C by 2 connected in parallel and connected to battery. The work done in charging fully both condensers is. So this is very simple. Just find out the equivalent capacitance. Equivalent capacitances, they are connected in parallel. So we have equivalent capacitance equal to Cp. Cp is C. Okay, they are connected in parallel. So equivalent capacitance is Cp, which is equal to C plus C by 2. Okay, we can say it is C plus half C. It is 3 by 2 C. Right. And therefore work done is equal to what? So work done is equal to half of Cp multiplied by V square, which is half of 3 by 2 C multiplied by V square. Okay, or you can say it is 3 by 4 CV square. Option B. Energy per unit volume for a capacitor having area A and separation D kept at potential difference V is given by. So Okay, here it's not epsilon naught. Okay, energy per unit volume, we know it is half of epsilon naught E square, right? It cannot be half CV square or half Q square divided by C, because this is energy stored in capacitor, total energy, not energy per unit volume. So it is either option A or option B. Right, it is option A, because E is equal to V is equal to E times D. So E is V upon D. Okay, so half of epsilon naught V by D square, which is V square by D square. Okay, so this is option A. This was very simple. A capacitor is charged with a battery and energy stored is U. After disconnecting battery, another capacitor of same capacity is connected in parallel to first capacitor. Then energy stored in each capacitor is. Okay, so we have seen in multiple questions that when you disconnect a battery, you have capacitor and you charge it. Then you disconnect a battery and connect another capacitance. What happens to the energy? It becomes half. Okay, so energy of these two capacitors is equal to what? Half of U. Okay, U dash is equal to half of U. But question is the energy stored in each capacitor is. So energy stored in each of them will be equal. Sum of the energies is U by 2. Okay. Therefore, the energy will be equal to what? U by 4. Okay. Half of this energy in each capacitor will be half of U dash. Total is U by 2. So both will have energy equal to U by 4. The energy stored in a capacitor of capacity C and potential V is given by. So this is the simplest question, right? It is half of CV square. Okay, find the capacitance as shown in the figure. So we want to find out capacitance of this thing. Okay, so here you have a capacitor and in d by 2, in half of the distance, you have filled a dielectric having dielectric constant K. So there is this dielectric slab. So what is the formula? So C dash is equal to epsilon naught A d minus T plus T by K. I think this is the formula. Okay. So let's find out the equivalent capacitance. It is epsilon naught A divided by D minus T. How much is D by D minus T? So T is equal to D by 2. Okay. So it is D minus D by 2. That is D by 2. Plus you have T by K, which is D by 2 divided by K. Okay. So it is, you can say, you can take this 2 in the numerator. So it becomes epsilon naught A divided by 2 times epsilon naught A divided by D 1 plus 1 by K, or you can multiply this 1, multiply and divide it by K, so it will be K by K, so it is K plus 1 divided by K, that you can take to the numerator. It is 2 times K epsilon naught A divided by D multiplied by K plus 1. So this is the formula. Sorry, this is the answer. Okay, it's option A is the answer. So yeah, this is direct formula. We had derived it, but suppose in case you don't remember it, what will you do? So in that case, the answer is very simple. See, suppose you don't remember it, then you have two capacitors here. So one is air filled capacitor, one is dielectric field capacitor. And how are they connected? They are in series combination. Okay, so air filled capacitor has distance between plates equal to d by 2. Okay, and dielectric capacitor also has distance between plates equal to d by 2. So see, the resultant capacitance C dash will be equal to, they are connected in series. Okay, so I can say 1 upon Cs is equal to 1 upon C of air filled region. Okay, 1 upon capacitance of air filled region plus 1 upon capacitance of dielectric region. So I will just call it Ck. So it is 1 upon epsilon naught A divided by D. And what is D? It's D by 2 plus 1 upon, it is epsilon naught K times A divided by D. And what is D? It's D by 2. Okay, take this D by 2 in the numerator because it is in denominator of denominator, right? So take this to numerator. So it will be d by 2. You have 1 upon Cs is equal to d by 2 epsilon naught A plus 1 upon, this is also d by 2 epsilon naught K. Okay, and then you can take this much common. Okay, it is d upon 2 epsilon naught A. I will take common. So it is 1 plus 1 by K, right? This is 1 upon Cs. So d divided by 2 times epsilon naught A. So it is K plus 1 divided by K. And if you take its reciprocal, you will get Cs, which is equal to K times D divided by, or did I do some mistake? No, sorry. If you take its reciprocal, you will get K times, you will get 2K times epsilon naught A divided by D multiplied by K plus 1. And this is the answer. Right? This is the answer. Got it? Okay, so even if you forget the formula, this is how you can solve. Okay, so instead of d by 2, thickness can be different. Okay, instead of d by 2, thickness can be different. Anyways, so let us see next question. A parallel plate capacitor with air as the dielectric has capacitance C. A slab of dielectric constant K and having the same thickness as the separation between plates is introduced so as to fill 1/4 of the capacitor as shown in the figure. Now new capacitance will be, so here thickness is equal to what? Not the thickness, the area. Okay, area is equal to 1/4 of A. T is equal to A divided by 4. Right. This is also T. Okay. So what do we get? So this is in parallel combination. Okay. So in this kind of questions, students often get confused. Okay. We shouldn't get confused. You can think of it like this. Okay. So this is your dielectric. Okay. So for this capacitor and this capacitor, the plates are connected to each other, both the plates. So this is parallel combination, right? So this area of the second capacitance is equal to A dash is equal to A by 4. Okay, it's written as T. T is equal to A by 4. So this will be what? 3 times A by 4. Okay, 3A by 4, because total area is A and the thickness is given by T. Okay, the distance between plates is T. So this is parallel combination. What will be the capacitance? Cp is equal to C air plus C of dielectric. Okay. So for air, it is epsilon naught A divided by D. But how much is area? Area is 3A divided by 4 plus Ck is epsilon naught K times its area, which is A by 4 divided by D. Okay. So, right. So then what you can do is you can take epsilon naught A by D common. If you take epsilon naught A by D common, you have 3 by 4 plus K by 4. You can take that 4 also common, 3 plus K. Okay. And then epsilon naught A by D. So without this dielectric, okay, a parallel plate capacitor with air as a dielectric has capacitance C. So without any other dielectric, its capacitance is C. And how much is that? Epsilon naught A upon D. So this is equal to C. Right? This is equal to C. So it's C by 4 multiplied by 3 plus K. Okay. So it's C by 4 multiplied by 3 plus K. Option A. So next question is parallel plate capacitor is constructed using three different dielectric materials as shown in the figure K1, K2, K3. The parallel plates across which potential difference is applied of area A meter square and separated by distance d meter. Capacitance across A and B is okay. So total capacitance is this is the question. So once again, so this one and this one, okay, where you have K2 and K3, they are in series combination. Okay, they are in series combination. So what is capacitance of series combination? We have 1 upon Cs is equal to 1 upon, you can say C2, if you call this C1, C2 and C3. 1 upon C2 plus 1 upon C3. That is 1 upon, it is epsilon naught Ka upon D. What is K? K is K2. What is A? A is A by 2. And what is D? D is also D by 2. So this upon 2 and upon 2 will get cancelled. Okay, similarly, we have 1 upon C3, which is epsilon naught K3 A3 by D3. And what is A3 and D3? It's A by 2 and D by 2. Okay, so what we can do is we can cancel out this 2 and we can move D in the numerator and we can take okay, many things common. So 1 upon Cs is equal to D divided by epsilon naught K. I will write it as epsilon naught A, right? And you have 1 upon K2. If you take these things common, 1 upon K2 plus 1 upon K3. Okay, so it is K2 plus K3 divided by K2 K3. And if you take its reciprocal, so you get Cs is equal to epsilon naught A multiplied by epsilon naught epsilon naught A upon D K2 K3 divided by K2 plus K3. So this much is capacitance of C2 and C3, the series combination. They are in series combination, right? So this part and this part, it is in parallel combination. Okay, this part and this part, it is in parallel combination. So what is the resultant capacitance? Cp is equal to C1 plus Cs. C1 plus series combination of C2 and C3, which is C1 is equal to, you can say epsilon naught K1 A1 divided by D1. And what is A1? So it is also filled in half of the sorry, half of the area. So A1 is also A by 2 divided by D1 is D. Okay, so epsilon naught K1 A upon 2D, you can say, plus this thing CS. Okay, so I will take it on next page. Take epsilon naught A upon D common. So what do we get? Epsilon naught A divided by D. We take common. We have K1 divided by, we have K1 divided by 2 plus K2 K3 divided by K2 plus K3. So this is the total capacitance. Let's check if there is such an option. K1 upon 2 plus K2 K3 divided by K2 plus K3. Option A, right? It is K1 upon 2 K2 K3 plus K2 K3 divided by K2 plus K3. Option A.